Hello everyone, welcome back to my channel. Today we are going to discuss about the classical gradient descent algorithm and its few classical problems. Now let us look more closely at what happens to the gradient during the classical gradient descent. The curve shown here represents our loss function, and our objective is to reach the minimum of this curve. Suppose we start at the point x and y1 on the right side of the curve. At this point, the curve is relatively steep. The gradient can be understood as the changes in y divided by the changes in x. So at this point, the gradient is delta y1 divided by delta x1. Now consider another point x2, y2, which is closer to the minimum. Here the curve is flatter, so the gradient becomes delta y2 divided by delta x2. From the figure, we can clearly see that delta y1 divided by delta x1 is greater than the delta y2 divided by delta x2. In other words, as we move towards the flatter region of the loss curve, the magnitude of the gradient becomes smaller. The parameter update in the classical gradient descent follows the idea xi plus 1 equals xi minus eta multiplied by delta yi divided by delta xi. Here, eta represents the learning rate. Therefore, when the gradient is large, the update is large. When the gradient becomes small, the updates also become small. This means that classical gradient descent automatically takes larger steps in steep regions and smaller steps as it approaches the optimum. However, this also creates limitation. When the gradient becomes very small near a flat region, the updates can become extremely small and the optimization process may become slow or even appear to stagnate. And this observation leads us directly to the next slide where the summarize the key behavior of the classical gradient descent. Continuing from the previous slide, let us summarize what we have learned about classical gradient descent. First, when the loss surface is steep, the gradient magnitude is large because the update depends on the gradient. This produces larger parameter updates. So gradient descent can move relatively quickly through steep regions. On the other hand, when the loss surface becomes flat or gently sloped, the gradient magnitude becomes small. As a result, the parameter updates also become smaller. Therefore, the classical gradient descent naturally takes large steps on steep regions and small steps near the optimum. This behavior is generally useful because we want to make careful adjustment as we approach the minimum. But there is also a drawback. If gradient becomes extremely small, the update may become so small that the learning process becomes very slow. The optimizer may need many iterations to make the meaningful progress. So the important takeaway is that large gradient means large update and small gradient means small update. This dependence on the local gradient is one of the important limitations of classical gradient descent. And this naturally brings us to our next topic. Can we modify gradient descent so that it can move more efficiently even when the gradient becomes small?